All right, what we're doing today is continuing this context-free grammar, non-deterministic machine discussion, and we're going to show that these two are the same. When we did finite state machines, we showed that they were the same as regular expressions, showed that they were the same as these linear grammars, and we made a big cycle of equivalence between them and the non-deterministic machines, and everything was all the same. And I even mentioned some other fancier versions that were all the same. Here, not everything's the same. If you take determinism for push-down machines, it's different than non-determinism for push-down machines. Non-deterministic push-down machines can do more. So the only equivalence we can really show here, and there is no regular expression at this level, so the only equivalence we can show is that context-free grammars, those are the grammars with the single non-terminal on the left side, that those are the same as non-deterministic push-down machines. Those really are the same. If you have a context-free grammar, you can come up with a non-deterministic push-down machine, and vice versa. If you have a non-deterministic push-down machine, you can come up with a context-free grammar. And that equivalence is a fundamental pillar of this level. What we're going to do today is this direction, because it's very, very logical, and it follows very, very closely on what Rusty did in recitation last time, showing you lect and yak. And it relates to parsing. So this direction is not only interesting from the theoretical point of view, but it also is interesting from the applications point of view. The other direction is actually not as interesting and is much more technically filled with detail, so I leave the other direction out. It's in the book. You can look at it, and it's worth looking at, but we just don't have enough time to spend on it, and it's probably the easiest thing to skip. So I'll show you this direction. Just take my word for the other direction. They really are identical. You can take a machine and convert it back to a grammar. It's a little ugly to do it. OK. The idea here is going to be, like I said, pretty logical. But at the same time, to make it easier, and to make it easier to describe, it's going to use Chomsky normal form. And this is the first of three main ideas like this that make use of Chomsky normal form, and is really the reason why we have Chomsky normal form in the first place. Somebody said, do you take grammars and really turn them into Chomsky normal form? Well, generally not, but you do use the fact that they can be turned into Chomsky normal form in order to make arguments and to come up with explanations and other algorithms. So here we go. I'm going to put a context-free grammar up on the board that's in Chomsky normal form, and we're going to talk about how we might turn it into a machine. And the method that we'll use will be completely general, but I'm going to motivate where it comes from and how its generality really works before we do this particular example. So here's the example of a context-free grammar. Let's say that A is the start symbol. So A goes to BC, and A goes to AB, and A goes to 1. There's nothing special about this grammar. I just picked it at random. Just your typical context-free grammar in Chomsky normal form. Start symbol, a few productions with double non-terminals, and a few productions with single terminals. No E productions, no unit productions, no long productions. OK. Now, I want to do an exercise that will help you understand this equivalence. We're going to turn this into a machine in just a minute, a machine that will accept every single string and no other strings except the ones that this grammar generates, a machine equivalent to this grammar. The way to understand how to create such a machine is to understand how to generate a string from this grammar, to kind of do what the yak tool was doing when Rusty showed it to us. Remember, in the yak tool, we describe the grammar, then we give it a string like that, and somehow it figures out whether this grammar can generate it or not. And then I said, Rusty, why don't you show them more or less how that works? And then he went into this long thread that went like 20 minutes long, showing you that it was looking at these symbols and keeping these things on a stack and deciding which one to get rid of. And any time that it got to a point where it had a choice, that's when that error would show up on the screen. You wanted to get a grammar that basically had no choice as to which production to do next. A grammar that was deterministically implementable at the machine level. Now here, we might not be able to get a deterministic version of this. There are a subset of grammars in CFG, in context-free grammars, called LRK grammars, that can be implemented by deterministic push-down machines. They're a very, very interesting collection. LRK grammars, and they are equivalent to the deterministic pushdown machines. We're not going to do that proof or talk very much about these grammars. It's a separate topic completely. And there were textbooks that used to have a chapter on this stuff, and they've kind of left it out, and they've kind of thrown it into the compiler course and taken it out of the theory discussion. But it was controversial for a while whether it should be discussed in detail at this level or not. And I think it's better not, because there's a lot of details there. But keep in mind that at least it's an important subset of the context-free grammars that relate to the most practical class, the deterministic machines. We're going to do a conversion here that goes to a non-deterministic machine. So a conversion where that yak tool would generally spit out errors saying, I don't exactly know which production to use here. We're going to build machines that don't know which production to use. The same way when we try to generate the string, we might not be able to figure out which production to use in order to generate that string. So let's go ahead and do it. We're going to try to generate that string. And I made this grammar fairly simple so that we're not going to have too much trouble guessing what to do. But you can see that you still might have to guess at some point. So we start with A, and we're trying to get 1, 0, 1, 1, 0. Let's do a leftmost derivation. In other words, as we guess which one of these to start with, we will always substitute for the leftmost non-terminal symbol that's still sitting. And you'll notice something very, very nice about leftmost derivations in Chomsky normal form as far as these forms or sentential forms that show up after the arrow. You'll notice this in just a moment. So let's begin. What do you want to start with? BC or AB? AB. All right. So now we got to generate something in place of that A. Well, we got two choices. Either we bump it up again or we substitute 1. Substitute 1. Okay, you guys are greedy matchers. So now we got 1B. All right, now what? Now AA, no choice there. Then what?
First A to BC. B to 0.
B to 0. All right, let's stop for a second. What do you notice about all these forms as we've been going along? Some special form they all have.
They're all terminal, terminal.
Right, they all have a whole bunch of terminals to start off, and then a whole bunch of non-terminals to end. And that's not an accident, because we start off with non-terminals. We're always substituting for the one on the left. We always substitute a single terminal. We never erase anything. It's Chomsky normal form. And these terminals start to accumulate at the beginning as we made substitutions for them. Meanwhile, the non-terminals still yet to be substituted for sit there on the right end. A long list of them that we haven't looked at yet. And in fact, the newest ones that get substituted in, like the BC that just got substituted in for A, what's the one we look at first? We look at the B to substitute next. So that A that sits there on the end, that just sits there and sits there and sits there at the bottom. And sooner or later we'll get to it, but we haven't gotten to it yet. Everybody notice that? Right, just something to notice. Let's keep going. How do we continue here? C to a 1. 1, 0, 1, C, A. 1, 0, 1, A. Thank you. Okay, now what? Now we're trying to get 1, 0 out of this. It shouldn't be too tough, right? A goes to AB. 1, 0, 1, AB. The A should go to a 1. Is that possible? Good. And the B should go to a 0. Okay, good. You did it. 1, 0, 1, 1, B. 1, 0, 1, 1, 0. Okay. Questions about that?
What was our goal again?
Up there.
Oh, right.
In general, this is probably hard to do.
Well, yeah, I mean, I made a grammar that almost anything you'd pick would work out. Here's another way. You don't have to copy this down. I just want to show you that there's another way. There's another leftmost derivation, a different one. For one thing, it starts with BC instead of AB. So whichever way you chose here would have worked, as long as you managed to continue correctly later. What does that tell you about this grammar? What's it called? What kind of a grammar is it? It's ambiguous because there's a string, I exhibited one for you, that has two leftmost derivations. That's an ambiguous grammar. The trees for these two would look different. Right? Ambiguous grammars are bad for parsers. They don't know what to do at any given step. And you would try to fix this grammar, if you could, to an unambiguous one that accepted the same language. But we're not talking about that right now. I'm talking just about understanding the parsing mechanism and the fact that there are choices here and the fact that I could have made this grammar harder so that the wrong choice, so that this actually would not have been able to get to the end here. We would have gotten stuck. We would have gotten up to a certain point and we would have said, oh, we can't do it. And in fact, in Chomsky normal form, you can count how many steps it takes to get here. There better be the same number of steps. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Same number of steps every time. It's always twice the length of the string minus 1. Okay, now why is that? It's because every time you try to get a string, there's got to be 5 steps that substitute capital letters for these things at some point. That's 5. That's the length of the string. And then you got to be able to get the capital letters in there to substitute for. You're starting with a single capital letter. Every time you use one of these double Chomsky normal form productions, you add an extra letter. So you're going to add 4 extra capital letters, so there get to be 5 extra capital letters. So that's n plus n minus 1, that's 2n minus 1, or 9 steps. It's always 9 steps. Chomsky normal form grammars are very easy to control. Okay, they're like in a straitjacket. They all work in a very specific way. So since there's only 9 levels to get to here, and at most 2 productions on a shot, worst case, we could do 2 to the 9th things and just try all the trees and figure out whether we could actually generate this string or not. And that's like a brute force, horrible membership test algorithm, but we could do it. We wouldn't have to try everything forever. And in this case, we would have found at least these 2 different parse trees that accept. All right, questions so far? So what we're going to try to do, we did this in our heads. We kind of saw how it was done. It was kind of ad hoc. We're going to try to build a non-deterministic pushdown machine that has the power to do exactly this or this. That it can simulate what we did, whatever choices we made. Now, you can definitely write a program to do this. We just described one that actually builds these trees and tries them all. But we want to build a non-deterministic program to do it that only has one stack, a pushdown machine. And the mechanism to do it won't be very complicated once you get started. And I think we can put it over here. Every time this grammar generates a symbol, the machine's going to read that symbol. All these capital letters that sit there waiting to be looked at and substituted for, where is our machine going to store those? Store them on the stack. And it's a nice lucky thing that we're storing them on a stack because it's exactly the data structure that's appropriate for these terminals, in the sense that C gets thrown on the stack, then B gets thrown on the stack. And what's the next thing that you look at to substitute for? The B, the left one. So the last thing that got thrown in is the first thing to be pulled out and get substituted for. So it's very natural to use a stack. Just think of the machine as taking these non-terminals, chucking them upside down into the stack, and the terminal symbols that you're substituting for, that's reading them on the tape. So let's be very specific and actually do it. The machine is not too complicated to write. We'll write it over here. The chalk is dustless because it has no integrity. All right. Here's what we do. We don't read any symbol to start. There's an empty symbol on the stack. And what do we put on the stack to start off? A, or the start symbol. That's what we're going to substitute for at the beginning. Don't read any symbol. Just remember that there's a start symbol that needs to be substituted for. So A, Z. And then you go to the huge processing state. There's only 3 states in this whole machine. Now, at any point along the way, say at this point, the machine would have already read the symbols 1, 0, and now it's looking to substitute for A. Let's write all the possible things that we might do in substituting for A. We might take A off the stack and replace it with BC. We might take A off the stack and replace it with AB. Now let's actually do that technically and specifically. Let's give the machine the possibility of choosing this or this. We don't care whether this is the right one or that's the right one. The machine's got to have the ability to do everything that you tried to do and everything that I tried to do. It's got to be able to do this or that. So it's got to be able to do all these things. All right. How do you take A off and put two new things on? Looks like this. And by the way, on what symbol are you reading when you do this? Are you reading any symbols? Are you generating any symbols in this grammar? Nothing. You're just looking at the stack and making substitutions. You do not move along the symbols at all. You don't generate any ones or zeros. So here's what we do. On an empty string, if there is an A on the stack, what do you do with it?
BC.
Right, you want to put BC on, but unfortunately our machine is too crippled to do this all in one step. So we first pop it off, right? Then what do we do? Doesn't matter what's on the stack now. Looking at nothing, no matter what's on the stack, we have to push on BC. What do we push first? Right, we need to push these things in reverse order, meaning not left to right, but right to left. First push in C, so that goes down, and then B on top of it, so that the next thing we look at is the left end. That's very natural. I mean, we want to push it in that way. C goes in first, B later, so that the next thing we look at is the leftmost symbol. So we push C on top of anything. We go to another state, and we finally come back, and we push, well, it's going to be C. We're going to push B on top of that.
Did you just say this machine only has 3 states?
Oh.
I mean,
I did say the machine only has 3 states. I did.
3 important states.
You mean like 3 states?
I feel like I'm in court. It's like
we go back to the tape.
It's just the worst thing. It's just like, didn't you say that you were thinking about your class when you were coming to that intersection? So how could you have been concentrating on the truck that was coming on the other side? I said I was thinking about, no, I meant, no. Michael's got a good question. I meant 3 important states. The start state, the processing state, and then the final state. It's true, but I think of these as technical states. And actually, all the other loops that we're going to do, I'm going to stop writing these states. I'm just going to say, you like push BC on. But you're right. You're right. It's technically not 3 states, and it could be much more. And thank you. These are just technicalities. Our machine can't do a pop and a double push in one step. It's got to do it in 1, 2, 3 steps. So I just want to show you can do that stuff. You probably knew it already. Popping and pushing twice, you can do in one step. Well, one conceptual step. All right. But just like I said, instead of writing all these things complicated on the board, let's make another loop that represents another 2 extra states that gives us the other choice. This is a conceptual loop, so I'll just put a green arrow. It should look more like that. And what do we do here? Didn't you say it had 3 states? What am I doing here in this one? Pop off A and push on. Right, so I'm going to say pop A, push B, push A. All right. That's it for A, right? Those are the only things you can do if you see an A on the stack. Except for that. Sometimes we don't want to expand the A. Sometimes we just want to turn the A into a 1. Did we ever do that? Right here we did it, right? How does the machine do that? How does the machine simulate that? For the first time, the machine will actually read a symbol. It'll say, if I see a 1 on the tape, then I can take that A off the stack and throw it away. And then I will read a symbol representing what that A generated in order for me to throw it away. Does everybody see the connection between the generating and the accepting? You're just turning this generation into a machine which is looking at the symbols that haven't been substituted for yet, put them on a stack, and then substitute for them one by one. If they actually generate a terminal symbol, you throw them away and you read a symbol on the tape. If they simply turn into two other symbols, you stay where you are on the tape, pop it off, put two new symbols on. So, if there is a 1 on the tape, and you have an A on the stack, you can pop it. Those three loops represent what you can do if there's an A on the stack. What else do we have to put on this big fat state? We'll call this the processing state, or the parsing state. All this is doing is parsing. It does just more or less what Yak does, except it doesn't know what the heck it should do at every stage, and Yak does because it uses a better grammar. What do you got to do for B? Right? Right? Pop B, push A, push A. And the other possibility is, if there's a 0 on the tape and a B on the stack, pop it. And then C, can you guys fill in C yourselves? Okay. Pop C, push B. And if there's a 1 or a 0 and there's a C on the stack, you can pop it. You can fill in the rest. There's only one more state because at some point we have to decide whether we accept a string that has gone through this long processing. So at some point we leave. How do we know we're ready to accept it? You're ready to accept something if what happens? The last symbol is read, R-E-A-D. Last symbol is read, and the stack is empty. So the last symbol is read means there's nothing left. The stack is empty means there's a Z back on the stack again. We filled it up with stuff. We knocked it all down. Leave it alone. And accept. Now there's no way the stack can ever get empty before, the stack can't get empty and then grow again in a Chomsky normal form grammar. Because of the way it's set up, there's no other non-terminals to possibly substitute for. They're sitting there on the end. So either you succeeded here or you didn't. And if you didn't, it means you made wrong choices along the way. Right. That's it. Are there questions about this conversion? This conversion can be done with any Chomsky normal form grammar. This is just an example. It could be done just as generally with any other thing we started with. Yeah, Mike?
How does the first state and the last state, how do you have an E? You come in with an empty on anything and an empty stack. You go. So if I just had 1 and processed if I had that string and I just processed the 1, why don't I go to the end?
Because you haven't taken up the 1.
I could.
Wait, you're saying what if there's just a 1? Is that what you're asking, Michael?
It's like that string.
Okay.
1, 0, 1, 1,
0. So you go here and you throw an A on the stack. And then you've read the 1 and popped it off. And now you say, I don't want to read any more symbols. The stack's empty. I'm going out here. But there's still more symbols to read. So when the machine tries to read the next symbol, it goes to some dead state.
Oh.
It's just like all those other machines. You've got to nail it down right here. And the implication is that any other movement in the machine will crash. So at this point, if there's nothing left, then you're safe. But if there's anything left, then you're in trouble. Okay. Make sense? Mm-hmm. Right. Your brother asked a question like that the other day, very similar. All right. Oh, look at that. It's so what a face he's making. All right. Questions about this? All right. Everybody's good? All right, consider this topic done. That's application number 1 of the Chomsky normal form and equivalence of context-free grammars and non-deterministic machines. We're going to move on. All right, I'll stop bothering you. No. You're bothering me. No. Oh, I don't like this green. There, dustless white. Another Chomsky normal form grammar. All right. Pumping lemma revisited. For finite state machines, we had this one tool that allowed us not to have to bring in the heavy guns of diagonalization to show that there was a set that was outside of the machines we were dealing with. The tool was called the pumping lemma, and it basically said, look, if you got long enough strings and they're supposed to be accepted by your machine, those strings will have loops in them in the computation, and therefore parts of the string can be pumped out, and you have to accept all of those too. And there's lots of sets that don't abide by that property. That you can show that no matter how the person splits them up, there are loops that if you pump them out enough, give you strings that are not in the set. And that's how we use the pumping lemma for finite state machines. And it was useful to show that certain sets were not regular. But here, if you try to do a pumping lemma for non-deterministic pushdown machines, something happens that's wrong. And let's think about that. If I have, say, some long string in a pushdown machine, like in that one I put up on the board before that had 3 states in it, that one. Say I run through a string that has, 9 symbols in it. I'm definitely going to have a loop in that machine. How come, let's say the loop was 0, 1, 0. And before it was 1, 1, and after it was 0, 1. How come I don't necessarily accept things like this? In a finite state machine, if I had a loop on 0, 1, 0, I would also accept this. Because when I came up to the next 0, 1, 0, I would do the same thing and end up where I was, and then continue on. How come in a pushdown machine this doesn't necessarily happen, and we're out of luck then? Because it also depends on what's on the stack. The first 0, 1, 0 might have changed the stack, might have put special symbols on it. And then when we came up to the same state, even though we're in the same state, there's different things on the stack, so we might not end up going in the same sequence of states at all. We might go somewhere completely different. So we've got this other thing that our decisions depend on, and therefore we can't pin down any kind of a loop in the computation just because we know that we got back to the same finite state. We would need somehow to know that we got back to the same finite state and the same situation on the stack. And that is a tall order, which we won't be able to do. We'll do something kind of like it, but nothing exactly that good. So basically this idea, look, whenever you come up with anything in computer science in this area, you always want to take what you know how to do and milk it for whatever you can. So you take the pumping lemma, which we kind of understand, and we go with it, and we realize there's this problem because the stack might send us in a different direction, and this actually kills this idea. It's like shoots it dead. You could try to fix that idea, but you'll try a long time and not get very far. We need a better way. So ironically, the way to find a pumping lemma in this level is not to look at the machine. The way to find the pumping lemma in this level is to look at the grammar. Now I might have shown this to you with the grammar for finite state machines too, but that would have seemed really artificial, since the loop just screams out in the machine and it doesn't quite scream out in the grammar. But here there is no loop in the machine, and there is one in the grammar. How do you get loops in grammars? I'll show you in a second. All right, so that's intro. We're going to do a pumping lemma to show that certain sets are not context-free grammars, and we're going to do it by looking at the grammars and the parse trees from those grammars. Questions so far? All right, yeah, Donna.
Does this have like another name besides pumping lemma?
No, it's called the pumping lemma for context-free grammars. There's the pumping lemma for finite state machine, and there's the pumping lemma for context-free grammars. And actually, there's lots of pumping lemmas. I mean, in the 60s and 70s, there were different variations of these pumping lemmas, and they come up for different things. And You'll see lots of different references. But they're all called pumping lemmas. All right, so for me to explain this idea and why you get this pumping lemma, you need to see an example. Otherwise, it'll just be too abstract and it won't make sense. So let's start with A, which is our start symbol, and write a parse tree up on the board here. You know, starting like this. A generates BC. BC generates BA. C generates AB. I'm going to keep going for a second, but before I keep writing, I want you to get a sense of where we're going with this. I'm going to write a parse tree down for a particular string. The string is going to be 1, 1, 0, 0, 0, 1. When I'm all done, this grammar can generate 1, 1, 0, 0, 0, 1. This is going to be the parse tree for that. And you're going to see the 1, 1, 0, 0, 0, 1 along the leaves on the bottom, where they would always show up in the parse tree. Now, in doing that, what you're going to find is that if you start at the bottom at one of these leaves and you work your way back up to the root, there's a unique path from every leaf back up to the root. What's going to happen is that path is going to be long enough so that one of these non-terminals, A, B, or C, is going to show up twice on that path. And that's where this loop quote will occur. Right, so that's where I'm going with this. I'm going to make this parse tree big enough to guarantee that if you pick any spot at the bottom and work your way back up to the root, that there will be a duplicate, that one of these non-terminals will appear twice. Right? I'll talk about that again in a second, but I just want you to know where we're going with it, and then I'll finish the diagram and we'll do it. All right, so this B generates 1. This A generates BC. This B generates 1. This C generates AB. BC. You need a big enough example to show this, so it's hard to do this with a smaller example. So stick with me here. It's not too much bigger, but it's still a little bigger. CC. Zero, 0. 0, 1. Oh, I lied. I meant 1, 1, 1, 0, 0, 1. I meant 1, 1, 1, 0. Now I didn't lie. 1, 1, 1, 0, 0, 0, 0, 1. 1, 1, 1, 0, 0, 0, 0, 1. Okay. So look at that, write it down, check it, make sure you get it, and we'll talk about where this duplication comes up in a minute and how the loop actually manifests itself. How many non-terminals here? 3. How long of a path do we need until we get a duplicate? 4, right? So, as long as I have a parse tree that's got a path of 4 or more, then I can find a duplication starting from the bottom working to the top. Let's pick a long path. Let's say down here. And I'll work my way up this way. B, A, C, A. The first duplication that occurs, I'm going to star these values. Here's the first one. Here's the second one. And I got some color here, so let me color these guys. There's number 1. There's number 2. So this is where we find our duplication. Not what's the first state that we come back to, like the finite state machine, but give me a long enough string, go down to one of the symbols here, work your way back up the parse tree, and the first non-terminal that repeats, star those 2 and remember those 2.
Why did you pick that one to go back? Is it just random?
Right. And if I had started here, it would have been C and C. And if I had started here, C and C. Right. Right. You can get different loops. But there's definitely one, and I just picked this one to show you. I picked this one for a reason because it illustrates it more generally than the other ones would. But the other ones would have been fine.
But it has to be from a path that has at least 4.
Right. Right. So you tell me this, since Donna mentioned that it's very, very important. How long should the string be to guarantee that I have a path of at least 4 in a Chomsky normal form grammar. And everyone understand what I'm asking? Because if I pick a string that's really short, I might not get a path of length 4. And if I picked a string that's just, 5 symbols, say 4 symbols long, I could have just emptied out the B, A, B right over here, and all the paths are length 3. I wouldn't have had a duplicate. So for short strings, you're not going to find duplicates, the same way you won't find them for finite state machines. You've got to have a string long enough. How long? Some exponential thing, some log thing? Which is it?
Well, the path is a log length, and so the length of the string needs to be...
So let's say the number of non-terminals is n. Give that a name. So n is 3 in this case. How long does a string have to be?
2 to the n.
Right. It could. The worst thing that happens is that it doesn't string out. You can't find long things. It's all bushy. They're all equal. So how far down would it have to go to guarantee a path of length 1, 2, 3, 4?
5 levels.
So
So that's
1, 2, 3. And I think 4 levels is okay, right? Because this could be the top. So 4 levels is okay. And that's going to mean 2 to the
2 to the n plus 1.
2 to the n plus 1. Some exponential number.
You don't have the leaves don't count in that.
Let's put it this way. Decide which way you want to do it, and it's either 2 to the n plus 1 or 2 to the n plus 1 plus 1. But the point is that it's exponential in the size, that the strings have to be pretty long reference to the number of non-terminals. So if I said, you've got 10 non-terminals here, the strings that end up having pumping in them for sure are approximately 1,000 symbols long. Okay, once you get a string 1,000 symbols long, I know there's going to be pumping in it, around 2 to the 10. Okay? I don't even care so much about the exact function. I just want you to realize that it's not a linear thing like it was for finite state machines, where the length of the symbols that have pumping is just longer than the number of states in the machine. Here it has to be longer than 2 raised to the number of non-terminals. Non-terminals don't act the same way like states did before. You have to get much longer strings. Yeah.
So it's 2 to the n plus 1, not 2 to the n plus 1.
Right.
Okay.
Right. Right. And I should just mention, actually, none of this really matters because once the details don't matter, I'll tell you why. If you're going to really use this pumping lemma, it's going to be used the same way we did it last time. I send Chris Walker home, I say, come up with a grammar, smarty pants, for this set. And he works all night long and he says, I got one. And I go, you're lying. And he says, no, I'm not, I really got one. And I say, how many non-terminals are in your grammar? And he says, there's 6 non-terminals in the grammar. I say, okay, and I just got to make sure, that I give him something bigger than like 2 to the 7th. I give him some big string. But typically, instead of me asking him, how many symbols are in your grammar, I can just say, well, tell me 2 to the number of symbols in your grammar. I can just tell him to do that exponential calculation and call that n and then work with that. I just have to get a string that's longer than some amount and keep the pattern right. And so I can hide that 2 to the n conversion and make him do it. All right. Well, we haven't even said what happens now that we got this duplicate. We just talked about that the strings have to be pretty long to get the duplicate. And we'll write it all down formally when we're all done. But let's first go through this one example. So again, Chris Walker goes home. He comes up with this grammar. I find a duplicate in the grammar. How do I prove to him that there are things that can be pumped up? Here's what we're going to do. And this is very much a grammar and a graph trick and a tree trick than it is a looping thing than it was before. Here's what we're going to do. See this thing? That's the tree that's rooted from the top one of the things that matched. I'm going to copy it over here. Don't copy it yourselves if you hate writing. I'm just copying this so you can keep thinking, and I can show you where it goes, and then you can look at it and make sense out of it in a minute. Okay, did I copy it okay? Looks all right. Okay, here's what we're going to do. I'm going to tell Chris to take this rooted part of his parse tree that's sitting at the top match and copy it over there. In other words, I'm going to tell him to generate another string. And at this point where he did BC10, I'm going to tell him, don't do BC10 this time. Do this instead. That's how I get this loop. And after he's done doing that, I can tell him, do it again here. And I can keep telling him to take this bigger subtree and put it in place of the smaller subtree. And that gives me longer and longer things. But before I tell him to do it many, many times, let's see what happens when he does it just once. OK, so now imagine that he actually did it, that he glued this thing right over here. That this is sitting here instead of this. Now let's try to read off the string that the grammar generates. There's going to be a bunch of parts to it, and I want to identify what they are. Let me put it here. We have the 1-1 part that sits outside of the whole thing. And we have the 0-1 part that sits outside of the whole thing on the other side. So 1-1, and I'll put 0-1 here. Inside here, we used to have a 1, 1, 0, 0, 0. I'm going to write that in because it's going to change. We used to have a 1, 1, 0, 0, 0. Sorry, this isn't outside. This is inside. There's only a single 1 on the outside, and there's a 0, 1 on the outside here. Thank you, Chris. So I got a 1, a 1, 0, and a 0, 0. What happens when I put this in place of the middle thing? Let's write it out and see. Let's first just write it out. Instead of 1, 1, 0, 0, 0, what do I get? I get 1, 1, 1, 1, 0, 0, 0, 0, 0. Say it out loud. 1, 1, did I do it right? Let's read it off. I'll read off the whole string. 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 1. Okay? Let me stop for a second. Does everybody see what I'm doing? I'll do it again. We're taking out this piece and we're putting this piece in its place. Right? And now we're reading the new string that it generates. So there's 1, 1 on the outside, followed by 1, 1, 0, 0, 0, followed by 0, 0, 0, 1. Right. What happened when we did this? Let's identify things that stayed the same and things that changed. This stays the same, doesn't get touched, and this stays the same. Nothing changes there. What's more, you see this little middle section here? That stays the same. How come? Because it still exists in this replacement. So what got changed? This part here, the left part of the big piece, not the middle part, not the part that's under the duplication, but the left part, that got doubled. And the right part got doubled. So this stayed the same. The 1, 0 in the middle stays the same. This stays the same. This guy got doubled. This guy got doubled. 1 turned into a 1, 1, and 0, 0 turned into a 0, 0. That's a duplication that occurs. It's not obvious when you stare at it until you actually do it once and watch the substitution and check. But if we did it again, the same thing would happen, except this would turn into triple 1s, and this would turn into 6 zeros. That's if we did it again. So this is a different kind of pumping, but it's pumping nevertheless. Instead of there being one loop in the middle that gets pumped an arbitrary number of times, there are 2 loops on either side of a fixed spot in the center, and those 2 loops get pumped simultaneously an arbitrary number of times. It's a different kind of a pumping, but it's something that still gives us a handle to prove certain things are not context-free languages. We're going to do examples of this. We're going to write it up formally and try to finish this whole topic before we are done today. So let me stop for a second. The logic so far is really important to get it down. And after this, it's going to become more mechanical and more example-oriented. So let me stop here for questions. Anything along the way here? It's a little complicated. What can I go over again?
Why isn't it enough that you have a simple recursion in there?
You mean that I can go forward, A goes to B something, B goes back to A something?
Yeah, or B goes to BA.
It is more or less enough. That's my short answer. It is more or less that. The way the pumping lemma works is that you have to have these duplications on any string that's long enough. So just because there's a recursion doesn't mean you have to use that recursion to get a long string. But if a string is long enough, then there's going to be some recursion used in order to have gotten to it. That's basically what this is saying.
Yeah, but
so it is kind of the
same. The question is, why isn't the fact that you can recurse, even if on any given string you don't have to, maybe?
Mm-hmm.
Why isn't the fact that you can enough to get the pumping property?
Well, I think it is enough. That's what.
Well, then I guess I don't understand why you
go through all this trouble?
Need a very long string, for example, or.
Oh, because the recursion might be a long way before you get to A might go to B, and B might go to C, and C might go to D, and D might go to AA. And then each of those is it's going to take 4 steps to get that recursion, but the string you've built in doing that is 16 symbols long. Right? So there's nothing wrong with the way you're thinking of it, except it still implies long strings before you actually hit that recursive loop. If you have something like, right? Yeah. Because each time you go to the next stage, you got to get rid of all these symbols.
So for the purposes of merely demonstrating anything with this, you need to think of it that way.
Right, but also, well, there's other issues too. The way you're thinking of it is you're kind of going forward to find this recursion. So like you would use these two where A doubles for the first time. And I'm kind of going from the bottom. The reason you want to go from the bottom is because, well, I should hold off because I don't want to say something that I don't mean, and I haven't thought about what the real issues are going forward rather than going from the bottom. But let me think about it, and I'll see. Because I thought I had the right reason why you wouldn't go forward, but I'm not sure. It's a good question.
If you're going forward and the first symbol happened to be the one that was repeated, you'd be like looping on your entire...
Yeah, but I'm not sure what's wrong with that. There's something nice about going backwards and going here, because then when you do the resubstitution, you get these duplications showing up here. And I'm not sure what happens if you start in the other direction. Maybe it would be fine.
Like the part that loops, the part that repeats would be like inside the string.
That's my guess. I think you're right. I think that if you start from the top, you don't get the repeating coming where you want, and it's not exactly what you mean. But I don't want to say it because I didn't check and I'm not sure. And it's a good question. It's certainly something that you might think about. You can hardly see this blue, huh? Can you, like blends in with the board. Other questions about this? All right, so this grammar really satisfies the pumping lemma. And as you know, I know that this string is in the grammar, and so is 1 to the 4th, 1, 0, 0 to the 8th, 0 to the 1. I can keep pumping these two sides up simultaneously as long as I want. And I know they're going to be generated by that grammar because it corresponds to a repeated substitution of this larger tree into a subtree of itself, duplicating the two side parts of the bigger tree, leaving the subtree fixed on the bottom. So these sections here, this and this, get duplicated. Let's call these different things. Let's call this piece U. That's the piece on the left side that's way out of the whole tree. V is the part that gets duplicated on the left. W is the part that gets duplicated on the right. No. W is the part in the middle. X is the part that gets duplicated on the right. And Y is the part that sits outside there. So every one of these strings is split into 5 parts. The U and the Y that sit on the outside of the whole big tree. The V and the X that are inside the big tree, but outside the smaller inner tree. And the W that's inside the smaller inner tree. The V and the X are the pieces that get duplicated every time. Or removed, right, because you could just take this out. Right. In other words, you'd have that 0 pumping like you have the other times. Don't use the loop at all. Don't use the smaller tree at all. Absolutely. You can definitely take the... Use only that smaller tree, right. Don't use the side parts at all, right. Take the smaller tree and just put it back there. And that just takes away the V and the X. So you can have a pumping of 0 times, absolutely. In other words, 1, 1, 0, 0, 1 should be in this language. All right. I want to write this pumping lemma down formally, but I just know when I do that everyone will just go into, all right, let's wait till the example. So let's do the example first, then I'll write it down formally after we've done at least one example of it. Let's use this to show that there's some set that isn't a context-free grammar. Do you know any such sets that aren't context-free grammars? Does every set we ever tried end up being a context-free grammar, context-free language? What do you think? What can't you do with a context-free?
The string that repeats itself.
The WW? Yeah, that's not. That's okay. We could use that one. I want to use a simpler one that's a little easier. Any others? It's true. WW is not a context-free language. Not Cfls. Here's the classic simplest not CFL. 0 to the n, 1 to the n, 0 to the n. 3 counts instead of 2 counts. If you do the normal thing, pushing these and popping these, then you're a little dead when it comes to checking that there's as many zeros as the ones you just checked for equality, because you popped them off and they're gone. You can go back if you had a two-way machine and handle this, but we don't have two-way. So there's no obvious way to do this. If I made any of these m not dependent on the others, then it would be easy to do. Right? You just read as many zeros as you want at the end. But if they all have to be equal, you can't do it. Let's use this idea of a pumping lemma to prove that you really can't. Not just our gut instinct, but there's really no way. You go home and work as hard as you want, you'll never do it. So let's do that. Okay, so I'll leave Chris Walker alone since he's been working hard on these impossible problems. And I'm sending you, Mr. Radcliffe, home to do the impossible. So Jeff goes home and he talks to his wife and he says, Shai gave me this really, really important problem and I have to work on it. And it's very important. And you need to help me. And she says, leave me alone. You do it yourself. And he comes back the next day and boom, he's got an answer. And I want to know how many non-terminals are in your grammar after you've turned it into Chomsky normal form. So pick a number. 4. So Jeff has 4 non-terminals in his Chomsky normal form grammar. That means I got to pick a string that is bigger than, say 2 to the 5th is plenty big. All right, so I'll pick something 2 to the 5th or bigger. Probably 2 to the 4th, 17 might be okay, but certainly this is big enough. So I ask Jeff first what his number of non-terminals is. Then I say, look, I'm going to give you a string longer than this length, just because I know that if I do that, you're going to have this duplication occur. And he agrees. We have this discussion. He's been here today, and he understands this, and he says, yeah, okay, I know there's going to be that duplication. Fine, go ahead, give me the string. So here's my string, 0 to the 32, 1 to the 32, 0 to the 32. Okay, that's my string. Right. Now look, when you write these proofs up, you can write it more formally. You can write it in a Dmitri way. Dmitri is a mathematician. He can write proofs. None of you are really mathematicians. It is harder for you to write proofs. So it is okay to write this proof just like we're doing it now. You can say, Jeff goes home and he tells me that his machine has 4 symbols. So I say to him, I'm going to give you a string that has more than 32 symbols because like we talked about in class, there's that tree and there's going to be that duplication. So I'm giving him this string, 0 to the 32, 1 to the 32, 0 to the 32. And then I ask him, Jeff, tell me which one of your symbols is the duplication. And then he tells me how that looks. Now, you can just write that out in English. It's a perfectly fine proof, and actually it convinces me that you understand it much better than if you try to imitate a more formal proof that you don't really feel is your language. Don't try to do the formality unless you feel like it's a convenience. If you feel like it's just something to do because it looks like the right answer, don't do it. Just write it in English. I'm completely serious. It's very important. All right, so look, you're looking at this, and now it's back to Jeff. I gave him the string. It's his turn. How is he going to tell me what this looks like? He can give me a picture, he can write it on the board, but there's a more specific thing he's got to tell me. He's got to tell me what piece of this string is the U, what's the V, what's the W, what's the X, what's the Y. If he does that, then I don't care what the picture looks like anymore, because I've got everything I need out of that. All I'm really going to get out of the picture is where the U, V, W, X, and Y are. So that's what I'm going to ask him right now. I'm saying split this into the 5 parts and tell me where these 5 parts are. Now, here's why you go from the bottom instead of the top. There's a criterion that he has to meet. Remember we started from the bottom when we found the first duplication? So there's a limit on how big this VWX part is. This VWX part comes after the first duplication. So that means the tree, the size of the tree is limited by a tree that's at most, n plus 1 height. So essentially, this VWX part is going to be less than or equal to that 2 to the 5th number. So that's one criterion. He can split it any way he wants into 5 parts, but the middle section, the VWX section, must be smaller than that 2 to the n, than that 32. And if we go the other way, we don't have that condition. It's much harder to do your proofs if you can't nail Jeff down and say that that middle part's got to be small. Is that... You're willing to buy that a little bit? Yeah. All right. You want to buy some dustless chalk? All right, that's what I want to hear. I want to hear mistrust. All right, so Jeff splits this into 5 parts. U, V, W, X, Y. And the VWX part has to be smaller than 32 symbols or equal. Okay? VWX, length of it is less than or equal to that 32. And by the way, the V and the X, they can't be empty. There's got to be some real V and X here. So I'll say the VX part has got to be at least as big as 1 symbol. One of these could be empty, and I could do examples to show you how that happens, but you can't have both of these be empty. How come you can't have both of them be empty?
Because then it's not a duplication, it's just the inner tree sitting at the bottom.
Right, because this has to split into 2 parts at the top duplication. One part goes down to the duplication. The other part goes out to something else. The other part is going to actually exist. That's going to be the V or the X. This part doesn't have to exist, right? I mean, the X could, well, one of them could actually not exist if this A, say I put the A on the other side. I switch this around. Then the V and the X get mushed together, and there's no other part to the right of the A. It's possible one of the sides can disappear, but it's not possible for both of them to disappear. Right? That's a technicality, but it results in this. The middle part's got to be smaller than or equal to 32. The V and the X on either side can't be empty. They've got to be at least 1. All right, so he's done this. So now he can do this any way he wants. From my point of view as the prover, I've got to be ready for anything here. So I'm going to let you change your mind as often as you want here, but you pick anything you want. You can split this up any place you want. So let's, being ready for Jeff's shenanigans and difficult way of splitting things up into 5 different parts, let's consider all the possible places where this VWX might show up. And let's think about the end game. Once he pins down where he wants the VWX to show up, I'm going to tell him how to pump the V and the X to convince him that it gets a string that is not of this form. So for example, if he picks the VWX all on the 0 part, then I just go, ha, 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 VWX all on the zeros? Are you kidding me? I'll just pump up the V and the X's once, and I get more zeros here than I have ones or zeros here. Right? Because the V and the X can't be empty, so if I pump them up once, it gets doubled. You can write that out more carefully in mathematics, labeling things and showing exactly how much bigger it gets, but you don't have to. You can just say, look, if the VWX part are all zeros, then when I make V2WX2, I'm getting 2 copies of V and X. One of them's got to have some zeros in it, so I get more than 32 zeros here, and none of this has changed at all. And that's a string that isn't in 0 to the n, 1 to the n, 0 to the n. So Jeff would never do that, but I handled it in case he did. Would he pick VWX in the ones? I could pump that up. I'd get more ones than the other side. Would he pick VWXs in this set of zeros? No, he wouldn't do that either because that's too easy. There's a lot of things he could do, but whatever he does so far, I've handled it. What else might he do? You'll notice, remember in the finite state machine, this was so much easier. You nail the guy in the first n symbols. Here, I can't nail Jeff down much at all. He can move this thing anywhere he wants. He can shift it left and right as long as it's only 32 symbols worth. But it's actually really important that it's only 32 symbols, because if it was like 64 symbols, he could beat me. How could he beat me if it was 64 symbols? What would he do? Straddle that one part, right? Could he do that?
Yeah, both sides.
Wait,
Can he really?
There'd be too many patterns.
Almost, right. It's tricky. But, well,
Alternating from 0 to 1.
right. You would duplicate a 0, 1, you'd get 0, 1, 0, 1. But, so I could still get him, but it would be more of an argument. But I could come up with examples where he could beat me if this was longer. If it were just like equal zeros, ones, and I can mix them any way you wanted, he could beat me then. Right? Because then straddling this, he could get equal zeros and ones coming up on every side. I'd be dead. By the way, equal zeros, ones, and zeros, that's not context-free either. But if we're using that language, Jeff could beat me. So I don't want him to beat me. That's why I nailed him down to less than 32 symbols. So we considered all the possibilities. Now, all in zeros, all in ones, all in zeros. And now what's left? He could straddle the border. So you got to handle all of these. And it's a long list of cases, and it's a tedious kind of thing. You just go through all the cases. If it straddles the border, then the V could be zeros, and then the X could be ones. And if you do that, it pumps these two up correctly, but it leaves this mismatched. If it was on this border, where the V was some of these ones and the X was some of these zeros, then it pumps these two up correctly, keeping them matched. Say there was 2 zeros here, 2 ones here, and 2 zeros here. It pumps them up right. But then this guy is mismatched. Right? Now what if it was the V equals right on the border, 1, 0, and the X equals, 0, 2? What happens there? That means right on this border. That's even worse, because the V's get duplicated. You get 1, 0, 1, 0, 1, 0. This gets duplicated 0, 0, 0, 0, 0, 0. And then it doesn't even look like of the form 0 to the n, 1 to the n, 0 to the n at all. You get these 0, 1s showing up. So anything that Jeff wants to do, if he mixes a V to have 1s and 0s in it, I win. If he has them be just 1s and these just 0s, and he uses this border, I win. If he uses this border, I win. If he puts them all in one of the 3 sections, I win. A long argument. It's long. It would be a page of just a tedious argument to convince everybody that no matter what he says, I can find a way to pump out this grammar of his and get strings that don't look like this. And then his grammar is not really doing what he said it was. All right, that's the pumping lemma for context-free languages. If you thought the other pumping lemma was tedious and long and annoying, this is more so. It just is. There's no other way around it. What I want to do is kind of write this up formally and then stop for some questions and recap. Pumping lemma for CFLs. It starts the same way the other pumping lemma starts. If L is a regular set, then all this is true. If L is a CFL, then all this is true. And the same thing happens with this pumping lemma. If L is a CFL, all this pumping stuff is true. But it's possible that if L is not a CFL, that all this pumping stuff is true anyway. Okay, this is not an if and only if. So just because you find a language and it pumps out right doesn't mean necessarily that it's a CFL. If it doesn't pump out right, then you know it's not a CFL. But if it does pump out right, it could either be a CFL or not. It's not a characterization, it's just an implication. All right, so if L is a CFL, there exists an n. This n is the number that you have to make strings longer than. So I'm going to put in parentheses just so you remember what it is. This is 2 to the n, where n equals the number of non-terminals in the Chomsky normal form grammar.
Wasn't that 2 to the n plus 1?
Yeah. It's 2 to the n plus 1 afterwards, but it doesn't matter.
You just make it bigger.
Just make it bigger, right. So there exists an n, and in particular, what is that n? Any n that's bigger than 2 to the n plus 1, where n is the number of non-terminals in the Chomsky normal form grammar for this language. Just make that note to yourself. That's what the n is. So there exists an n such that for every string, for every z in L, where the string is bigger than n, the string is long enough, bigger than that size, there exists u, v, w, x, y equals z. So there exists a way to write the string like this, such that vwx is less than or equal to n, vx is greater than or equal to 1. So this is Jeff's turn. He gives me the number. This is my turn. I give him the string bigger than that number. This is Jeff's turn. He splits it into 5 parts according to my restrictions. And now this is my turn. For every I greater than or equal to 0, u, v to the I, w, x to the I, y is also in L. Welcome. Welcome to the front. All right, let me look at this again. Big, ugly lemma. Simple, nice, elegant idea behind it, but just hard to write down. I'll read it out. If L is a CFL, the following is true. Let's call this the pumping property. There exists an n. That n is anything bigger than 2 to the n plus 1, where n is the number of non-terminals in the Chomsky normal form grammar. There's some n. That's how you get it. For every single string in the language that's bigger than that n, this has to be true. There is a way to write that string in 5 separate parts, concatenated together equaling the string. The middle 3 parts smaller than that n. The second and fourth part together not empty. Such that every single one of these v's and x's, as many times as you want to pump them, if you pump them up that many times, u, v to the I, w, x to the I, y, pump them up as much as you want, those strings are also in the language. That says it. Now, if that's not bad enough, the way you use this is you run a negation sign through it. Remember, if this isn't true, then that's not a CFL. So how do you say that this isn't true? It means for every n, there exists a string such that for every way you write it in 5 parts, there exists some I that shows that that string is not in L. We run through that negation just like we did with finite state machines. And that's the conversation I had with Jeff, is that negation of this. I'll write that down just so everybody gets it, so I don't just blab it out in 8 seconds like I did. Let's write it down. I'm going to run a negation sign through this. That's how you use the pumping lemma. You show that the pumping property doesn't hold. So running a negation side through that says that for every n, he picks the n, I have to respond to it. There exists a z in L, z bigger than n. That's my job. I exhibit the string. Remember, he picked the n, he picked 32. I exhibited the string, 0 to the 32, 1 to the 32, 0 to the 32. This is the commentary. This is the theory. Okay, this is what actually happened. That's the script. Then it was Jeff's turn. He wrote this in 5 parts. Now here there were many possibilities, and I considered many cases. The VWX could have been in the zeros. They could have been in the ones. They could have been on the second set of zeros. They could have been on the border. Many cases. All these possible cases for VWX. For every one of them, which I did I use? I always used 2. I always pumped it up one more time. I didn't need any different I's. It is possible that for different cases I might have to use different I's in a more general, harder proof. But this one was easy, and every single time he picked a place for the VWX, pumping it out just once, that means I equals 2, was enough to make sure that I got a string that wasn't of the form 0 to the n, 1 to the n, 0 to the n. So there exists an I such that u, v, I, w, x, I, y is not. Finally, the not comes through in L. All the not does going through here is reverse the quantifiers. Finally, it shows up and reverses a statement. That's how you use the pumping lemma. And if you're going to write proofs like this and describe them, don't look for the formality to give you a better grasp of what's going on. Look for the story. Write the proofs like this story and do the cases in detail. Even if it ends up that it takes 2 pages to write it out, at least it'll be a flowing, easy 2 pages. You might be able to write it out in 3/4 of a page in more formal ways, but you might not even understand what you're doing when you're done. And I don't want to discourage anybody from using formality. If you like it and it makes you feel better and it makes you feel more in control, then do it. But if it makes you feel like, oh my goodness, now I'm trying to describe something that's very hard for me to understand, and I'm going to do it in Greek because at least there I won't feel bad about not understanding it, don't do that. Use the language that really makes the most sense to you. And if it's just English, that's fine. Mathematicians use fancy language because they want to publish more papers before their tenure clock is over. And if they just wrote in English, it would take too long. That's not too far from the truth. No, because you gotta communicate faster, more efficiently. It takes too long to write math out in prose. I mean, Euclid wrote math out in prose. He didn't bother coming up with lots of notation. But it's a little harder to read his stuff. And if you're going to talk to somebody a lot, you come up with a common vocabulary. Every group has its own vocabulary, as annoying as that can be to people outside the group. All right. Questions? Yes, Neil.
Our first pumping lemma, couldn't we have done that in terms of grammar also with the same parsing tree? And
yes. Yes, we could have. We could have done the same grammar. And remember, linear grammars, they're like all lopsided on one side. The grammar is very, very special looking. And if we would have found the loop, it would have been just like this, where all the pumping happens on one side and a single non-terminal sits on the other side. And it would have been equivalent to what we did with the machine. But I think it's more intuitive to do that. I've never actually done this. I've never actually pretended that the pumping lemma had nothing to do with machines the first time and just did it with grammars just so that when I got to this, it would seem more natural. I never did that. But one day I'll probably do it and then get an idea of whether it really works or not. But sure, I could have done that. I could have shown it to you with a grammar, and then this would have just been, hey, we got a more complicated grammar this time that both sides can generate terminals. You know, there's pumping on both sides. I don't know if it's good or bad. But the first pumping lemma is so much more natural just to think of loops. And the idea is so technical and ugly that you don't want to obscure it with anything else. So, I don't know. Other questions about this? Right, let me show you one thing, and then we'll quit today, or I'll stop for final questions. This is a major technique to show that languages are not context-free languages. And luckily for us, most of the interesting languages are context-free languages. All the programming languages that you write in are context-free languages. That's very good. That's how we have compilers. But there's other ways of showing things are not context-free. I could bring in diagonalization again, the big jackhammer, but you'll see that again at the Turing machine level, and I'll remind you of how it works, so you don't have to see it again right now. But the idea of closure is useful here too, and it saves you going through this pumping lemma so many times. You really don't want to go through this pumping lemma too many times if you can help it. I mean, it's a nice idea to know that it exists, but using it too often is kind of annoying. And after all, there are some languages that are not CFLs that the pumping property does hold for them. So you can't even use the pumping lemma to show that those aren't context-free languages. So you need some other technique. Here's one other technique that's just like the one we use for finite state machines. The idea of using closures to show that things are not CFLs. So what's a good example of this? I wrote one down here that I like. Oh yeah, here's a good example. You know what? I need this. I got to use 3 symbols for this one. 0 to the n, 1 to the n, 2 to the n. This is definitely not context-free, and the argument is exactly the same as what we just did before for 0 to the n, 1 to the n, 0 to the n. It's the same exact pumping lemma proof. This we know is not context-free because of the pumping lemma. Now let's consider this equality. This equals the set of all strings that have an equal number of 0s, 1s, and 2s. That means mix them any way you want, but when you're all done counting them, same number of 0s as 1s, same number of 1s as 2s. Okay? Everyone understand this language compared to this? All right. Well, this is equal to this intersect with what? Intersect, same equal property, but here they have to come in order. So 0 star, 1 star, 2 star. Okay? Everybody with me so far? The intersection of these two equals this. Now, we don't know the status of this language. We know the status of this language is not a CFL. We know the status of this language. This is what? This is regular. So it's certainly a CFL. Certainly a CFL. It's even regular. And this is the unknown. Now, what do you know about intersections of CFLs? Do they have to be CFLs? No, they don't have to be. It's unfortunate. There's very few things that CFLs are closed under compared to finite state machines. We use the same trick on a finite state machine. Equal 0s and 1s, 0 star, 1 star, 0 to the n, 1 to the n. And there, since finite state machines are closed under intersection, we could conclude, since this is regular, and 0 to the n, 1 to the n is not regular, then there's no way equal 0s and 1s could be regular, because if it was, then regular intersect regular would give you regular, and we know that's not regular, therefore that can't be regular. But here, we have this unfortunate situation where intersection of two context-free languages is not necessarily a context-free language. I mean, here's the proof of that. These are both context-free. Use a stack to push and pop, read 2s. Read all the 0s you want, use a stack to push and pop. Each of these is context-free. Take their intersection, what is it? 0 to the n, 1 to the n, 2 to the n. Things that are in common with all these are things that they're all the same. So here's two context-free languages. Their intersection is a non-context-free language. Contradiction to the fact that context-free languages might possibly be closed under intersection. They're not. So if they're not closed under intersection, it's just too bad. This is not a context-free language. This is. This
Still
might be, or it might not be. We can't conclude anything. If we knew that their intersection had to be a context-free language, if they were both context-free languages, then we know this for sure would not be a context-free language because this isn't. But we don't know that. Too bad. That really sucks. All right, class over. No. There's one nice result for context-free languages. That they are closed under intersection, and here's how it works. If you intersect a context-free language with a regular set, not with another context-free language, but with a regular set, then you're guaranteed to get a context-free language. The way you'd say that in math world is that context-free languages are closed under intersection with regular sets. It doesn't mean this. It doesn't mean that if you take a context-free language and a regular set and you intersect them that you get a regular set. That's not true. It doesn't mean that if you take a context-free language and a regular set and you intersect them that you always get, I don't know, a non-deterministic machine. But it does tell you that you get a context-free language. You're not necessarily going to get a finite state machine, but you're going to get a context-free language. If this is context-free, you can't say anything. But if it's regular, then you get context-free. That's nice. If we know, I just take my word for that that's true. I'll convince you in a minute. Take my word for it. If that's true, then if this were a context-free language, then its intersection with a regular set should give you a context-free language. But its intersection gives you this, and we know this is not context-free. So our assumption that this was context-free can't be right, and therefore equal zeros, ones, and twos is not context-free. So this identity implies that equal zeros, ones, and twos is not a CFL because CFLs are closed under intersection with regular sets. CFLs are closed under intersection with regular sets, so this identity implies that equal zeros, ones, and twos is not a CFL. If it were, then its intersection with a regular set would give you a CFL, and you don't get one. All right. Are there questions about that kind of idea? You can use closure to show other things are not CFLs, starting with things that you know are not CFLs by the pumping them and then building up closure arguments to get other things. Here's one of the most interesting examples.
Is that just because you can build a product machine with a pushdown machine and a finite state machine because you don't have to worry about there being two stacks? There's just...
That's exactly it. That's what I want to do in the last 10 minutes. That's exactly it. Very good. You all get that? How could you? Right. When we talked, this is last 10 minutes and we'll go, then lunchtime. When we took two finite state machines, how did we intersect them? We kind of simultaneously kept track of where we were in both machines, keeping states that had pairs of states in them. And when we were all done, we looked at the pairs of states, both of which were final states, and we circled those. And that new machine accepted all the things that were accepted by both my first machine and my second machine. It was called the product of the two machines. Did Dimitri do that? Did he do the product?
How many states? Wait, did that have m times n states or two?
It had n times n states.
Oh, okay.
Mm-hmm. You could also do it another way. You could do intersection by a combination of unions and complements. But that requires more of an exponential jump because you end up having to do a non-deterministic combination. So you wouldn't really do it that way if you didn't have to. The thing is, though, that the intersection of two machines, you're basically keeping track of where you are in two machines. Now, there's only a finite number of places. I can be in 10 places in this machine, 8 places in this machine. This machine's got 10 states. This machine's got 8 states. So I can keep track of the 80 possible combinations there might be for me to be in a different place in this machine and in this machine simultaneously. And that's what I do. I make a new machine with 80 states, and I remember where I am in both of these machines, and I keep track. And on a 0, I remember what pair of states I go in there, and on a 1, I remember what pair of states I go to, and then I see which states have both final states in them. And I circle those double, make those final states. It works without too much trouble. So why can't we do that with pushdown machines? Why can't I just keep track of what state I'm in this pushdown machine and what state I'm in this pushdown machine and go fine? Well, you actually can do it as far as the states go. If I have a 5-state pushdown machine and a 6-state pushdown machine, I can make a 30-state pushdown machine and keep track of where I am in each machine and have a pair of states. There's no problem with that. And the arrows go to the pairs of states just like they did before. So where does the problem show up? The problem shows up with a stack because I'm only allowed to manipulate one stack. But each of these machines have their own stack. It's like two people getting married and they each want a closet. And you only got one closet in the room. You know, your whole life you got two closets. So my wife got the closet in my room. I don't care. I keep stuff in the drawer. But these machines care a lot. They want their stack, right? Give me my stack. Don't take my stack. So they got to manipulate their own stack. This machine's got its own stack. This machine's got its own stack. Don't touch my stack. So if you're going to make one machine to handle both of these, you can't have one stack simulate two. Well, maybe you could. Go home and try. Can't do it. You can't have one stack simulate two stacks. Some of you might think, hey, wait, what if the stacks only used one symbol? Then could I have one stack handle two stacks that do one symbol? Well, there's a lot of, but these stacks don't have one symbol. They can have as many symbols as you want. Arbitrary stack, you can't simulate two of them with one. You only got one stack you can use. So this product construction breaks down. And that's what Chris was saying before, very succinctly and very accurately in 1 minute. That's what he said before. He said, oh, is it because when you take the product, well, I forget how he said it. He said it better than I would have said it. But you get stuck when you take two machines and do this. On the other hand, what if one of the machines didn't have a stack? It threw its stack away. It doesn't want a closet. It's just a finite state machine. Then everything's fine. Because you do the construction just like you did before, and on the arrows, you just put in the manipulations for the one stack that stays. So you can intersect context-free languages and regular sets by using a non-deterministic pushdown machine and doing its product with a finite state machine. Okay, writing all that down formally is kind of ugly. Doing a particular example isn't so ugly. I mean, it's probably worthwhile to do a particular example and see what happens. But when you do it, you can always do it constructively and come up with a context-free language because there's only one stack you have to take care of. All right. There's other things that context-free languages are closed under. We'll talk about them a little bit. We have 1 or 2 more days to talk about this whole area. There's one more main thing I want to do. I want to do the membership algorithm that takes polynomial time for deciding whether a string is actually parsed. Okay, and this is whether it's non-deterministic or not. So you give me a non-deterministic machine, a grammar, I can do it in n cubed. Okay, remember we said that Yak doesn't like not to have a choice, and it seems like it's crashing. It doesn't have to crash, and it doesn't have to go exponential. You can still do polynomial time parsing with a non-deterministic machine. You just have to be careful. If you want to do really fast polynomial time parsing, like linear time, then you got to get down to deterministic LRK machines. All right. One last thing. When we talked about closure, and we'll talk about this next time again, deterministic machines and non-deterministic machines differ as to their closure. Neither one of them is closed under intersection, but deterministic machines, are they closed under complement? They are. The same reason finite state machines are. You just toggle the states. Non-deterministic machines are not closed under complement. Toggling the states doesn't work there. It doesn't correspond to the complement language. They happen to be easily closed under union. Non-deterministic machines are closed under union because you just do an e-move. But deterministic machines, they're not closed under union because you're not allowed e-moves. And you can't just do a grammar trick like this. That's good for non-deterministic machines, but if you add this to a grammar, then it's no longer an LRK grammar. If you wonder what LRK is some big complicated definition, that violates it. All right, so unions aren't closed for deterministic machines. Complements are, vice versa for non-determinism. There's a lot of other operations. We'll talk a little bit about them, some of the techniques, review this idea, and then move on to the membership algorithm and finish up decidability stuff. So probably 2 more lectures to finish up with context-free grammar level, move on to Turing machines.